I request Dr. Amit Kumar sir to start a presentation.
Okay, thanks, Dr. Ravinder. I hope I'm audible.
Yes, sir, you are audible, sir.
Okay, and kindly enable the share because I want to.
Yes, sir. Yes, sir.
Project, yeah. Good evening, everybody. I hope all of you have received the material that I had used yesterday. So if you have any questions, maybe we will take a pause in the middle after 1 hour maybe, and then we can have some further discussions. I mean, if you want on the topics discussed yesterday or the topics that I'm going to discuss now. Okay. So
sir, sorry to interrupt.
Sorry, yeah.
Actually, I haven't shared the material I have received. Today night I will be sharing.
Oh, okay, okay.
Okay, sir. Thank you, sir.
Okay, thank you. Let me share my screen and please let me know when the screen is visible.
Yes, sir. Screen is visible, sir.
Okay, excellent. Okay, so I think I will start from where we left yesterday. And yesterday when we were talking about, we talked about multiple things actually. We started from the basic perspective of human learning, and then we talked about the 3 types of human learning. We talked about how those 3 types of human learning, like self-learning and learning by guidance from expert, and learning by indirect guidance. So all those things map to machine learning. And we also understood the process, the overall process of machine learning. And after that, what we also started discussing, and we are going to continue that discussion today, is when we execute a machine learning project, right? I mean, and that is what exactly all the data scientists are doing. So what are the different activities? What are the different steps or phases that it goes through, right? So yesterday we started with it and we could talk about a few steps as a part of the phase preparing the model or preparing to do the model, right? Which basically relates to collating the data and then understanding the data quality and the different aspects of the data by exploration. We have seen how we can explore the data either using the, yeah.
Sir, your voice is little low. Can you increase?
Oh, is it? Is it better now?
No, sir. Means your mic, you should take it near.
Oh, I see.
Little near.
Is it better now?
Yes, sir. Little better. Yes, sir.
Okay. Please let me know whenever it gets low or something. Please let me know. Okay.
Sure, sir. Sure, sir. Thank you.
Thank you. So then we also talked about different problems like the issue of missing data, the issue of outliers, and how we can, what are the different strategies that can be taken to address them, right? So we talked about all those things. The only couple of things that we didn't talk about, and we are not going to talk about today also, because this is a topic which is going to be covered by Dr. Goswami tomorrow, is the dimensionality reduction and the feature subset selection. That portion of the data preparation is going to be discussed tomorrow in details, right? But other than that, we have talked about the different activities to be done as a part of preparing to model. So now what we are going to talk about today are the subsequent stages, right? The subsequent phases rather. What are the phases? The learning phase, after the learning is being done, the performance evaluation, and thirdly, if there is some need to improve the performance, then how the performance can be improved, right? So these 3 things are the ones that we are going to cover today. And these are very, very important concepts. So I want everyone to please follow each one of them, because these are like foundational concepts in machine learning. All the other things that we do as a part of machine learning, like selecting some kind of a model and then applying it, those are much trivial. But understanding the concepts that we talk about today are the most important parts of machine learning. So let's start with the first thing, which is learning. But before that, let's go through a few very, very vital definitions which are going to be used very often. So first thing is data set. When we talk about a data set, we say input data set, or we say training data, we say test data. So all those things, when we talk about, then what is that actually means? So a data set, basically, it means a table. I mean, all of us, or maybe most of us are familiar with a table, right? So if I just take a very trivial example of a table and I try to draw it. So say, for example, this is like a table where there are different columns, right? So if I talk about a student table, like the different columns would be, say, roll number, the student roll, right? Then the next column may be something like a student name. Then we may have the grade of the students, right? So grade in a particular subject, subject 1. Then the grade in the subject 2. Okay, so all those things we capture, grade in 3, subject 3. And finally, we have some kind of a overall evaluation, right? So overall grade. So grade overall, right? So this is something we do. And when we have that, we have these in the form of several columns which represent the different attributes. And we also have several rows, right? And each of these rows represent one student. Say, for example, student 1, we have student 2. Like this, we have several students up to, say, there are n number of students. So student n, right? So these are the different rows. The columns are the different attributes or the characteristics of the student, and the rows are the individual students, right? So that constitutes a data set. And when it is used to induce a model, or what we call to train a model, then that portion of the data is called training data. Okay, we are going to come into more details of that, but just remember that when we refer to a data set or simply data, we mean that table, which is constituted of attributes and the rows or the instances. We call them instances. Okay. The next thing that is very important are the instances. So what are the instances? As we talked about, the different rows are called the different instances. So the row 1 for student 1 is the first instance. The row 2 for the student 2 is the second instance. The row n for the student n is the nth instance, right? So these are the instances. And then we have the features, okay? So that's the other, okay, one more thing. The instances are also called observation, they're also called examples, or they are also called data points. So you will see different machine learning literature call these rows or instances by a different name. Some may call it as an example, some may call it as an observation, some may call it as a data point. Even I might be using the different terms, but all of them mean the same thing, the instances. The same way, the features, okay? The features are the columns or the attributes, okay? So they refer to the attributes. And there is one more very important aspect. So these attributes which help in deciding. So there is one attribute which is finally used for the gradation. And the grade which might be assigned maybe A, B, C, and all those grades, right? And these grade might be decided based on the values which are there in the different attributes. Okay, these attributes are called features, or they are also called predictors. Okay, they are also called predictors, and some people also call them as independent variable. Okay, this is also called independent variable. In the same way, the last column, generally there is the last column. It might be different in a different data set, but in most of the data sets, you will see that the last column is the column for which we need to come up with the label. Okay, that is called the target variable, or it's also called dependent variable. Like these ones are called independent variable. The last column is called the target variable or the independent dependent variable. Okay. And last but not the least, there is something called prediction. So what is the prediction? Say, for example, if I have the different instances xi, and based on the feature values or the predictor values of the different instances, we come up with the value of the target outcome yi. Okay. So what I mean to say is, say there are the different values for these features, and there is one value for this target variable. We call this as y, we name this as y, the target variable, and all these predictors as x0, or we may call it as xi, sorry, not x0, xi. Okay, so the first one will be x1, the second one will be the second attribute will be x2, and so on and so forth. Okay, so what we try to do is, so this y is dependent on the values of the x's. Okay, so if we have a perfect condition, we can have a function f, okay, which is based on this xi. Okay, which is based on this xi. So we say that this dependent variable y, the value depends on these independent variables xi, and there is some function which is applied to it. Now, what machine learning tries to do is, or any algorithm of machine learning tries to do is, it tries to approximate this function. Okay, it tries to approximate this function. Okay, so what it does is, instead of this f, it comes up with some f hat, okay, or f cap, which is very close to f, or which is supposed to be very close to f, but it might not be exactly the same as f. Okay, so f cap or f hat is an approximation of the function. Which function? The function which can get us the value of the target variable from the value of the predictors. Okay, so that is the f hat. And since this is not exactly f, what we get as an outcome is f hat of xi. Okay, f hat of xi, which is y hat, which is the estimated or the predicted value of the y variable. Okay, so this is denoted by this y hat. Okay, so when we say that we are trying to predict, what we are trying to do is, we are essentially trying to make a guess of the value of y from the values of xi. Okay, so we are trying to come up with an estimate of this function f, which helps us derive the value of y from the value of xi's. Xi's are the predictors, and y is the target variable. But since it is not exactly equal to f, we are not able to exactly get the function f, and we are getting an estimated function f. That's why the value of y is not also exactly equal to the y. It is y hat, or estimated y, or what we call is a predicted value of y. This is a very, very important thing, and all of us should be very, very clear about this picture. This picture of a data set, what are the different features, which are the predictors, and which is the target variable, what are the instances or the data points or the attributes or the variables. All these concepts need to be very, very clear with all of us, okay? Because when we go forward, we are going to use these terms very often, okay? So,
Sir, one of the participant request is to repeat once again training data.
yeah, I will actually come to the training data in one of the subsequent slides, okay? So
Sure,
I'm not
sir.
going to cover here because that needs to be very, very clear. We need to understand what training data means. So I'm going to cover that as a subsequent slide, okay?
Once again, I request you to take your mic little bit near, sir, please.
Oh, okay. I am not sure how I can do that. Is it now okay?
Yes, sir. Perfect, sir. Now perfect.
Okay, now I'm actually holding the mic in front of my mouth. I mean, that's the best I can do. Okay, anyway, so let's move forward.
Thank you, sir.
So now,
Thank you.
yeah, thank you. So now we will come to modeling. We will often come across these terms, modeling and model, okay? So what's a model and what's the modeling? What do we mean when we say modeling in context of machine learning? So first coming to model. What is a model? So basically model is basically a machine learning algorithm. Okay, whenever we refer to the term model, basically we are referring to one of the algorithms, and we are going to look at what all algorithms are there. We are going to name a few of them, and in tomorrow's class we are also going to look at closely at a couple of algorithms, okay? But model, when we say model is nothing but it is an algorithm. And what is an algorithm? All of us know, right? Algorithm is nothing but a set of steps, okay? A set of steps being implemented as a computer program, right? So model is nothing but a set of steps, or rather an algorithm. And what is modeling? Modeling is basically selecting a particular algorithm and then making it customized or making it kind of aligned with the input data set. Okay, so what we do is we take an input data set, which is basically in context of supervised learning, it's basically the labeled data set, and that labeled input data set we use to align or to customize our machine learning algorithm or our machine learning model, right? So this is basically what is known as modeling. Now, what are the different models in machine learning? So the first one, when we talk about supervised learning, again, we are going to talk more about the two variants of supervised learning. There is one variant called classification, and there is another variant called regression. We are going to cover that very soon. But some of the algorithms or some of the models which are very, very popular are k nearest neighbor, naive Bayes, decision tree. There is some model which is known as support vector machine. Then there is something which is known as a random forest. So there are some very, very popular models in classification, which is a type of supervised learning. Likewise, for regression, which is another variant of supervised learning, the popular models are simple linear regression or multilinear regression, logistic regression, and stuff like that, okay? For unsupervised learning, a very, very popular model is the K-means model, which is a clustering model, okay? Clustering is one type of supervised learning. Again, we are going to cover that very soon. And K-means is an algorithm which is very popular for clustering, okay? And there is some other algorithm or model called market basket analysis, okay? So now let's go to the supervised learning, and let's first talk about the classification. Okay. So what is classification? So just remember, we talked about two different types of data, right? One data we talked about was the qualitative type of data or the categorical data, right? Which are basically the nominal or the ordinal data, right? Basically some name or some order like grade, okay, A, B, C, D, or say, for example, blood group. Okay, again, it can be A positive, B positive, and stuff like that. So that is all categorical data. And we also talked about some data which is called quantitative or numerical data, right? Quantitative or numerical data. So just remember one thing, when we have got the target variable, so we have the predictors and we have got the target variable, right? So when the target variable is of type categorical, that means the target variable can have discrete values and discrete non-numeric values in general, right? So those, in that case, supervised learning is also called classification. And what we try to do here is nothing but we have a set of labeled input data, which is also called training data. Okay, it's a labeled input data, and we use this data to train our classifier or the classification model. And once we have that classification model ready, what we do is we apply that classification data on some unlabeled data, the data which have just the predictor variables, the values for the predictors variables. The value for the target variable is not there. So the unlabeled data, we apply it on the unlabeled data. Okay. And what we try to come up with are the labels for those unlabeled data. So for each instance, we have the value of the predictor variables, and based on the value, we apply the model on those values and we come up with the label. Okay, so that way, an unlabeled set of test instances, we generate the labels for them. Okay, and those labels are of type categorical. Okay, they have the type categorical. In that case, we call the type of learning as classification. Okay, say for example, when we are trying to predict the say for example outcome of a game as a win or a loss, right? So that means the target variable is the outcome of the game, win or loss. That means that type is basically a categorical type. It can have only two values, win and loss, and both the values are non-numeric values, right? So that is the classification. That problem is a classification problem, right? And the same thing when we have the target variable as a numeric variable. Okay, say for example, the target variable is the rainfall, the amount of rainfall. So the instances are the days for each day, the different values for each day. Okay, and what we are trying to predict or the target variable is the rainfall, the amount of rainfall, how many millimeters of rainfall is going to happen. Okay, so what we provide to the model is the input data which has got the values of the predictors and also the value of the target variable, which is the quantity of rainfall. And we are going to train a model, a regression model. Okay, in that case, it will be a regression model. And what we get as an outcome is instead of the labels, we get a particular value. We get the value of rainfall. So given a set of days, okay, so day 1, day 2 to day n, we have the different parameters or the different predictor variables we have the value for them, and we apply the model on that. And what we get as an outcome is the amount of rainfall which is predicted to happen. Okay, so we are going to have that as the outcome. So when we have the target variable as a categorical data type, we have that problem, that type of machine learning problem is called a classification problem, or that kind of a model is called a classification model. And when the target variable is of numerical data type, then in that case, the problem is called a regression problem. And the model that we adopt for that is a regression model, right? A typical regression model would look like, I will come to that. It is, I mean, for example, we can have a linear regression model where we have just a straight line which can give us, the model is just a straight line, okay? We are going to look into that. Looking at it in a more trivial way, the training data is going to have something like this. It is going to have a set of pictures, okay? And it is going to have a set of labels for a classification problem. And the pictures, when it is the picture of a duck, it is going to have the label as duck. And the picture when it is of, say, of a rabbit or a porcupine, the label will be not a duck, okay? Not duck. Or it can also be like when we have a binary classification, we can have like this. When we have a multi-class classification, then we may have, for this we may have a rabbit, and for this we may have the third one, we may have a porcupine. Okay, so we may have like that. And the test instance, what will be coming as a test instance is just a new image. The image without the label value. And what the model will do is, for this image, it will predict what should be the label. And it will predict that the label should be of a duck. Okay, so this is in a very trivial way we try to understand a supervised learning or a classification, how it works. Okay, so this is the training data, and based on the training data, we train a model and we get a model, aligned model. And then when we give a test data or a test instance and we apply the model on the test instance, we get the label as an outcome. Okay, and the label tells me whether it's a duck or it's not a duck. I hope this is clear with all of you. Let's move on. So this is regression as I talked about. So there will be a lot of training images or training data. Okay, training data. And based on the training data points, we will try to fit a linear regression model or a straight line having an equation alpha plus beta x. Just remember in our high school days, we used to look at the equation y is equal to mx plus c, where m is the slope and c is the intercept. It's basically the same thing. And if we have multiple variables instead of one predictor, if we have multiple predictors, obviously it is going to be m1 x1 plus x2 plus m3 x3, where x1, x2, x3 are all the predictors, and m1, m2, m3 are all the coefficients, right? So what we try to do is we try to come up with the model which is nothing but a straight line equation, something like y is equal to 3x minus 0.5. This is the model that we come up based on the particular data which is given as the training data. Okay, so what we do is we use the training data, and based on the training data, we come up with the values for M and the value for C. And this is exactly what is known as model training. This is what we mean by training a model. We have a generic equation of a straight line. That is my regression equation. But from the training model, we have to arrive at the best suited values for beta and alpha. This is what we do by model training. After training, we get a very, very specific straight line equation like this one. Okay, so this is what we mean by model training. Now let's look at unsupervised learning. So here there is no concept of training data. Here there is no concept of labels. What we try to do, we have got an input data or an input data set. And what we try to do, say for example, each of these different objects, they represent each of the instances in the data set. Say this is instance 1, this is instance 2, and like this is instance, say for example, n. Okay, say there are n instances. Okay, what we try to do as a part of clustering, which is a specific type of unsupervised learning, is we try to group or cluster the similar instances together. Okay, so what we do is, say for example, the rectangles represent a particular type of instances. Okay, say for example, yesterday we were talking about this customer segmentation, right? And we talked about the platinum, the gold, the silver, and say the bronze categories, right? So say for example, each of these shapes, this represent one of these categories. Say these rectangles are the platinum category, these circles are the gold category. Okay, the ovals are the silver category. Okay, and these triangles are the, say, bronze category. Okay, so what we try to do is, based on certain notion, based on certain algorithm, like k-means is one particular very popular algorithm, we try to group the instances together. So what will happen as a result, maybe we will have one group, say having instance 1, having instance say 5, then instance 7 as one group, and that group say maybe is the platinum group. Okay, then we may have another group, say for example instance 2, instance 6, instance say 8, all of them belong to the say gold. Okay, like this we segregate all the instances into 4 different groups, and these groups are the platinum, gold, silver, and bronze groups. Okay, so like this we try to club up or cluster the different instances based on certain notion. Okay, what notion we are going to discuss when we talk about the algorithms of clustering. Okay, and in a very similar way, just looking at it very trivially, the same images, right? We have the same images. What we do as a part of clustering, we club up all the ducks, the images of all the ducks together. And we club up images of all rabbits together. And we club up all images of porcupines together. Okay, so here we are not coming up with any label, because label is something which needs to come in as a past experience or the training data. We don't have that. We are not talking about supervised learning. We are talking about unsupervised learning. Here, our objective is just to group the similar instances of the data set together. And how do we do that? We are using some algorithm, some clustering algorithm like the k-means algorithm. And what we do as a result, we group or we cluster all the duck images together, all the rabbit images together, all the porcupine images together. Okay, this is what we do. This is what is called clustering, which is one form of unsupervised learning. Same way, there is one more form of unsupervised learning, which is called association analysis. Okay, what does it mean? Say, for example, our data is a transaction data. Transaction data means, say, for example, I go to a retail store and do a transaction. Basically, I purchase different items. Okay, I go and purchase some breads. I go and purchase some milk. I go and purchase some eggs, and so on and so forth. Okay, I purchase some items. So all the items together along with the quantity and the price, that gives my transaction data. Okay, that transaction data is something similar to this one. Okay, like this we have multiple transaction data. And what the role of association analysis is, it tries to match the items in the different transactions. Say, for example, in transaction 1 and transaction 2, these items are in common. Okay, same thing applies for transaction 4. These items are common. Okay, here I have been representing the items by a different shape. So what we can say is there is an association between transaction 1 and the transaction 2 and the transaction 4. Okay, like the same way we can see that transaction 2 and transaction 3, they have these two shapes in common. Again, transaction 5 also has this shape in common. So we can find an association between transaction 1 and transaction 2 and transaction 5. Okay, so what we try to do as a part of association analysis is we try to find out the association between the different transactions based on the different items which are part of the transactions. Okay, so this is the association analysis, and one type of one algorithm used for association analysis is the market basket analysis. Okay, so this is what is the other form of unsupervised learning. Now we go to the third different type of machine learning, which is the reinforcement learning. Again, we are not going to cover this particular type in much of details, but the bottom line is just think there is an environment and there is an agent. What is the agent? The agent is that particular, what should I say, that particular object which is trying to learn something. Say, for example, as we talked about yesterday, a toddler is trying to learn how to walk. So that toddler is that agent. Okay, and there are certain actions, and each action can have either a reward or a penalty. Okay, so there can be a reward or there can be a penalty associated with every action. Okay, and that is decided by the environment. And what is the environment? Say, for example, for the toddler, we had a particular room full of different obstacles, right? And if it comes across an obstacle, it will fall down. So falling down is not suitable, right, for the task walking. So it should try to avoid the obstacle. So when it falls down, a penalty is assigned. And whenever a penalty is assigned, the policy, there is a list of policies, that policy list gets updated. Okay, whenever there is an obstacle, mind it, you will get a penalty. So avoid that obstacle. Okay, that is the policy which is being updated. Like this, there can be different other actions, and for each action, either you can have a penalty or a reward. So like this, it builds, it keeps on taking different action, and it keeps on adding to the policy list. Okay, so that at the end, it kind of learns the whole process of working seamlessly without committing any further error. Okay, because wherever it can come across some error, it has already added to the policy as a penalty item, right? So it always tries to avoid that particular action which can result in a penalty. Looking at it in a more trivial way, say I have a robot, okay, that's my agent, and my environment has two different things. One, either you can have a fire where you can burn yourself, or two, you may have a source of water which can give you a comfort feeling. And if the robot walks towards a fire, it burns its hand, and immediately it assigns some penalty points. And it knows it's a bad thing, it's a bad action. Next time you need to avoid this option. Okay, this action needs to be avoided, and that way it updates the policy. And this keeps on happening. It keeps on taking multiple actions, and based on whether there is a reward or whether there is a penalty, it keeps on updating the policy. Okay, so this way it keeps on learning by itself. So this is the third variant of learning, which is known as reinforcement learning. Now, I will want all of you to take a attempt by yourself, trying to figure out what type of learning each of these is. Prediction of the result of a game. What we are trying to do, we are trying to come up with a label. What is that label? Whether there is a win or loss. Win or loss, what type of target variable is it? It is basically a categorical target, right? So that means, first of all, it's a supervised learning problem, and at the same time, it is a classification problem because the target variable is of type categorical. Next, lead segmentation. Lead means for any sales initiative, you might get a list of prospective customers. That is known as lead. Okay, in the jargon of sales, it is called a lead. So when we are trying to segregate the leads based on the quality of the lead, right? What are we trying to do here? Are we trying for a supervised learning problem? No, because we are not trying to label anything, right? We are just trying to segregate a group of instances, okay? Or rather, a set of instances into multiple groups or segments, right? So we don't have a target variable, right? So what we are trying to do here is unsupervised learning, and that also we are trying to do here is clustering. We are trying to cluster. Okay, it's called clustering. Now the next one, fraud detection, right? What we are trying to do, we are trying to detect whether a particular transaction is a fraudulent transaction or not. That means what we are trying to do, we are trying to label a transaction as a fraud transaction or as a normal transaction. Okay, I mean legitimate transaction. That means again, we are trying to label the transaction as fraud or legitimate. Okay, either we are assigning a F or we are assigning a L. That means again, we are trying to get the label of some unknown instances. And that label is of type categorical. That means we are looking at a supervised learning problem, which is a classification problem. Okay, so we are looking at a classification problem. Next, price prediction of stocks. Again, we are trying to predict or we are trying to come up with a value of the target variable. What is the target variable? Price of stock. What is that price of stock? What is the type of it? It is basically a numerical value because price is going to be a number, right? And a continuous number, right? It's a numerical value. So that means it is also a supervised learning, but it is not a classification. It is a regression problem, okay? You need to adopt a regression model to solve this kind of a problem, right? Now the next one, self-driven car or the driverless cars. What do we have here? Are we trying to decide on the target variable value or are we trying to find the label of an unlabeled instance? No, we are not doing that. Are we trying to group together certain instances of the data set? No, we are not doing that. Then what we are trying to do? We are trying to self-learn. What is self-learning? Basically through trial and error or basically through actions and reward and penalty, we are trying to update the policy list. Okay, so that is what we are trying to do. That means It's a type of reinforcement learning. Okay, so this is how we can come up with the different types. Again, demand forecasting, what we are trying to do, we are trying to forecast or predict the demand. Demand of what? Certain item. And item means what? It can be breads, it can be butter, it can be anything, it can be clothes, it can be anything. And what is that number? It is the quantity, right? We are talking about the quantity. And that quantity is a numerical value. So basically, when we are doing demand forecasting, what we are doing is supervised learning. And again, we are going for a regression problem, right? We are trying to predict a target variable which is numerical in type. So we are trying to solve a regression problem. Okay, hope all of you understand that. And why is it important? Why is it important to understand what type of problem is it? What type of problem are we looking at? Because as the first step, we need to select a model. And how do we select the model? Based on certain things. Okay, what are the certain things? The certain things are, what are we trying to predict something, or are we trying to group something or associate something? If we are trying to predict something, is that prediction or the target variable, is it of type category, or is it type numerical? So based on that, we can have either a classification model, we can choose a classification model, or we can choose a regression model, right? And in case it's not a prediction problem, we are trying to do a grouping problem. We are trying to solve a grouping problem. Obviously, we have to pick up a clustering model like a K-means, right? So basically, whenever we are given a problem, we first need to understand what type of problem is it. Is it supervised or unsupervised? If it is supervised, is it classification or is it regression? If it is unsupervised, whether is it clustering or are we trying to do association analysis? Okay, so based on that, we need to select the algorithm, or what we call, we need to select a model. Okay, and then only we can go for training the model. But first of all, we need to select the model. So these are some of the different types of tasks that we can go for, like for classifications. These are the different models that we can pick up. For regression, these are the different types of models that we can pick up. Then for dual use, both for classification and regression, we can pick up neural networks, which is a very, very a special type of model, right? Then we can also go for a support vector machine. Again, it's a very, very special type of model. We can use both for classification as well as for regression. Same way, we can go for different clustering models like K-means, like K-medoids. These are different clustering models. We can pick up, there is a model called DB-scan. So those are different clustering models. We can pick up clustering model based on what type of clustering are we trying to achieve, right? And second thing, whether are we trying to do clustering or are we trying to do association analysis, right? This is where we do. Okay, so I hope all of you have understood this till this point, and how we can actually, what are the different types of learning, and what are the different types of machine learning, and what are the different models that can be used, and how we can decide the different problems, what type it belongs to, and based on that, we can select a model, right? Now, once we select the model, what we need to do next is we need to train the model. And how do we need to train the model? Basically, we need to do the training based on a process which is called a holdout. Okay, what is the holdout process? See, one thing we need to understand is, I train a particular model, right? So very fair. We have the input data. Based on the input data, which is the label data, and I'm talking about, when I'm talking about training, I'm talking about supervised learning, okay? I'm not talking about unsupervised learning. because in case of unsupervised learning, there is no, there is no question of training. Okay, so when we are training the model, we are talking about an input data set is being there, and that input data set is basically a labeled data set. Basically, it has a set of instances which has both the predictors and the target variable value, right? And that data set is called a labeled data set. Now, say for example, I train the model based on the input data set. Okay, I use the entire input data set. Now I train the model. Now, how would I understand whether the model which has been trained, it is a good or a bad model? How do we make that out? Okay, for that we need to have a set of test instances, but those test instances also need to have the actual value of the target variable, because whenever we have the actual value of the target variable, only then we can compare that with the predicted value of the target variable. So I have a set of actual values of the target variable, and I have a set of predicted values. Say TA is the set of actual values and TP is the set of predicted values. And I can obviously say from common sense itself, if the actual value is close to the predicted value, okay, that means my model has done a good job. And if for most of these instances, so these are the different test instances, I1, I2 to say IM. Okay, these are my different test instances. So if for most of the test instances, I can see that for the actual values are matching with the predicted values for the model design, then I can say that the model has been trained in a very good way. But if there is a lot of mismatch, then we can say that the model training is poor, or the model is a poorly trained model. But now comes the $1,000,000 question. If the test instances, we do not know the target, the target variable, the actual values of the target variable, how can I make the comparison? And if I am not able to make the comparison, how can I evaluate the performance of the model? So that's the reason why we cannot use a completely new set of test instances. What we have to do is the input data set, we have to bifurcate. We have to group it, we have to segregate it into two portions. One portion is called the training data. Maybe say if there are 100 instances as a part of the input data set, I keep 70 instances to train my model, and I keep 30 instances to evaluate how good or how bad is my trained model. Okay, so how do we do that? So I have the training data, which is 70 instances. I pick up some model. Say, for example, I pick up the KNN model. Okay, and then when I pick up the model, I basically use these training instances to train this model. Or say, for example, I use the naive-based model. Okay, so I train my naive-based model using these 70 instances, which are my training data. Okay, and once my model is trained, I apply my model on the test data set, which are the 30 instances. For each of the 30 instances, we come up with the predictions, the target variable values predicted. And for each of those, we also know the actual values, because this is the part of the input labeled data itself. So we can definitely do a match of them. So I can compare the actual value. This actual value is also called ground truth. Okay, this is my reality. This is my Bible. Okay, this is my ground truth. So this ground truth, which is there already as a part of my test data set, I compare this ground truth with my predictions. The predictions which come by applying my trained model on the test instances, just the predictors of the test instances. So I compare the predictions with my ground truth, and based on that, I come up with a matrix. And we will look at that matrix. That matrix is called confusion matrix. We will get more deeper into that confusion matrix. Okay, and then we can evaluate how good my or how bad is my trained model. Okay, so this is the process for model holdout or the data holdout and model training. Okay, so I select a model based on the problem I have in hand. Then I take the input data set, which is a labeled data set for supervised learning. I break it into two pieces or segregate it into two pieces. One piece I use for training the model. That is my training data, which is say 70% or 80%. That is my own strategy, how much portion I use as the training data. And the remaining portion, which is the test data, which is the 30% or the 20% of the data, I use it to test the efficacy or the goodness of my trained model. Okay, by comparing the ground truth value or the actual target value or the actual value of the target variable with the predicted value. Okay, and based on that, we come up with something which is called a confusion matrix, which is specifically in case of the classification problems. We will look into that, and then we figure out how good or bad our training is. Okay, or our trained model is. This is the process of training the model. Now, one thing that we need to understand is I take the data set, okay? I take the data set and divide it into two portions, like what we talked about, right? We divide the training data set. Say, for example, this is my whole training data set. Okay, there are multiple instances, okay? And from these instances, I pick up a few and mark them as my training data. Say, for example, I randomly pick up these few data and I mark it as training data. Okay, and the remaining data are my test data, like this one, all these are my test data, right? Now, just to understand one thing, when I am picking up the training data from the input data set, this is my whole input data set. When I am randomly choosing my test instances, or when I am randomly choosing my training data, right? In that case, it is quite possible that some elements of the input data, some variability we call it, of the input data is not being captured as a part of the training data. Okay, so what may happen is my training process may not be good enough. I will give you a very trivial example. Okay, say for example, I have my instances. There are different class values. So the different class values are A, B, C, and D. Okay, say I pick a particular training data where I have instances having class values A, B, and D. The C is missing. Okay, so now when I'm trying to do the classification for this instance, which has the label C, I'm going to have a challenge with that, right? So that's called the variability. The variability is not captured properly in my training data. So how can we address that? So to address that, what we do is something known as cross-validation. So what we do is I divide the training, the input data, I divide into multiple folds or multiple compartments. Okay, say for example, I divide it into K folds. So in that case, my cross-validation is called K-fold cross-validation. If that value of K is equal to 10, That means I divide the whole data set into 10 folds. So if I have, say, 100 instances, and if I divide that into 10 folds, that means each fold will have 10 instances, right? And each of these 10 folds will be completely randomly picked 10 folds. Okay. I'm not going into the details of how to do that random picking because that's a completely different discussion altogether. Okay. So I am dividing the whole data set into 10 folds, and each fold has 10 instances. If my total number of instances is 100, and each time what I do is I take one fold as my test instance and the remaining 9 fold as my training instance. Okay, or training data. Each fold is my test data. Okay, and the remaining 9 folds is my training data. So I keep on repeating this process. So first time I take the K1 fold as my test data and the K2 to K10 as my training data. Then next time I pick up K2 as my test data and K1, K3 to K10 as my training data. Like this, I keep on changing. So I have 10 iterations. Each time I pick up a different test fold or rather different fold as test data and the remaining folds as a training data. Okay, this is how we can come across or we can overcome the problem where a portion of the input data is not being considered as a part of the training data because of the way the training data is selected. Okay, this is called K-fold cross-validation. So you can see this here. I mean, each of the beads or each of the circles represent one instance. So every iteration I am taking, so this time I'm taking fold 1, this first thing, then I'm taking this fold 2, and I keep on changing the fold. Each time I take one fold as my test data and the remaining all the other folds or all the other instances as my training data. This is the essence of K-fold cross-validation, which is a very, very important concept in machine learning. A very, very similar but a little different is something which is called bootstrap sampling or bootstrapping. Okay, here also we derive different training data, but the way we derive it is a little different. I don't know how many of you are aware of the concepts of sampling theory. Sampling theory is a concept in statistics, and we can draw samples from a population, and the samples can be drawn as simple random sampling with replacement and simple random sampling without replacement. Okay, what I mean to say is, say for example, I have a bucket of objects. So when I'm trying to do a sampling, each time I am picking up one particular object from this bucket, and I'm building the sample here. Okay, when I'm doing a simple random sampling with replacement, I pick up one object, I put it here, and again I keep it back. Okay, I just mark. Say for example, this is 1. I mark here 1 and I put it back. So next time, again, I can pick up 1. Or I can also pick up some other item, say this one, which is, say, for example, 3. And I can pick it up as a part of the sample, right? So in bootstrapping, what we do is basically simple random sampling with replacement. So each time I pick up one sample, I put it back again. So next time I can pick up the same sample again. So here, if you look at the input data set, I have 2 blue dots, 1 yellow dot, and 2 each of green and brown dots. But here, if you look at it, we have 1 blue dot, 1 yellow dot, 2 gray dots, or 2 brown dots, sorry, but 3 green dots. That means either one of them has been repeated thrice or one of them has been repeated twice. Okay, so I have repeated the sample. Okay, this is called bootstrap sampling or bootstrapping. Why is it used? In certain cases, what happens is I have a shortage in my training data. My training data set is not big enough. Okay, so in that case, what we do is we do bootstrapping to kind of improve my training process, my model training process. And that's how we kind of do the bootstrapping to improve my model's performance. Okay, so this is called bootstrap sampling or bootstrapping. So what I will do is I will take a pause at this and take some questions, and then I'm going to go to the next logical part of the discussion. Okay, so let me take some questions. Dr. Ravinder, if you can take some 2-3 questions, we can talk. Dr. Ravinder? Dr. Ravinder, are you there?
Yes, sir.
Okay, so can we take a couple of questions?
Sure, sir. Sure, sir. Sir, first question. Please discuss the trade-off between bias and variance.
Okay, so we are going to look at that right away. I mean, after this, we are going to cover bias and variance right after this.
Okay, sir. Next. Kindly repeat one more time regression, sir.
Okay, regression basically, when the target variable, when we are doing a supervised learning problem, obviously we have a input data set, which is a label data set. Label data set means the target variable value is known, right? And when the target variable is having the type as numerical, that means it has a number value. Then in that case, the type of problem is known as the regression problem. Okay, typical cases that we look at are, say, for example, demand forecast or rainfall forecast, or when we forecast the stock prices in the stock market. So those are cases where the target variable is a numerical value, right? It's a continuous value. So that case, we go for regression.
Next question. Please provide some idea about parameter optimization in genetic algorithm. How this can be made.
Okay, I will take a note of that, but I don't have a plan to cover that as part of today. Let me see if it can be covered as a part of any of the subsequent days. So parameter optimization for genetic algorithm. I will just take a note of this. Okay. Okay.
Next question, sir.
Yeah.
If we do not have any ground truth, then how can we train or compare the model?
Exactly. And that is what we have discussed just now. We have to hold out a part of the input label data set as the test data. Okay. And based on the test data, and for the test data, we have the ground truth, right? So using the test data, we have to evaluate the model.
Next question. Are folds and clusters the same thing?
Sorry, what is the question?
Are folds and clusters the same thing?
Not really. I mean, though I use the term very loosely, actually, when we talk about folds in k-fold cross-validation, we basically mean to say a set of instances, right? So we segregate the whole, or rather we pick up from the whole data set, we pick up a set of instances, multiple sets of instances, as each of the folds. Whereas cluster, we generally use when we talk about grouping similar instances together. So though I use the terms loosely, in k-fold cross-validation, what we mean to say as folds are basically sets of instances. Okay.
What is the difference between k-fold and bootstrapping?
Okay, so k-fold cross-validation, when we are doing, we may or may not use, basically we are supposed to use sampling without replacement. In general, we do sampling without replacement. So basically the same instances we don't have repeated as a part of the training data. Whereas in bootstrapping, we do sampling with replacement. So one training data set may have an instance repeated multiple times. As we can see in the slide here, we can have one instance repeated in the same training data set itself. Okay, so that is bootstrapping. So it's basically the difference between simple random sampling with replacement and without replacement. Okay. Okay, I think now we need to pause, because again, otherwise we are going to run out of time and we have a lot of things to cover. We need to cover the evaluation of models. Okay, once we are done with that, again, we can come back for the questions. Okay.
Sure, sir. Sure, sir. Thank you, sir.
Thank you. Okay, so now we come to the next part of the discussion. So when we train a model, okay, there can be different situations. One is we are trying to train a very simple type of model. So here the extreme case which is given here as an example is we have a non-linear data set and we are trying to fit a linear model or a straight line model to differentiate the instances of a non-linear data set. This is one extreme. So we are trying to have a very, very simple model to the work. Okay. Obvious outcome will be when the model is trained and it is applied on the test instances, lot of cases there will be a misclassification or a wrong labeling being done. Okay. So this is one extreme case. This is called underfitting. By using a very, very simple model, we underfit. Okay. The other extreme case is we go for a very, very complex model like this one. Okay. A very, very high order polynomial which can segregate each and every instance in a very, very precise way. Okay. So here what we see is a set of instances is exactly segregated. It is 100% accurate. Okay, this is called overfitting. What is the problem with each of them? In the first case, when we have an underfitting case, or when we pick up a too simple or a oversimple model, what we have as a result is many of the predictions, they are not going to be close to the ground truth. Okay, this is one thing. The second thing is when we have a very, very complex model or a case of overfitting, what will happen is for the training data, since it is fitting the model based on the training data, accuracy will be very high. Okay, and if I am having the test data aligned with the training data, in that case also accuracy will be very high. But what will happen is, in case if the training data changes, okay, the predictions will be way different. So the models which are going to be fitted on different training data sets are going to be very, very different, right? So what will happen is the predictions are going to be less accurate, less different from the ground truth, but at the same time, each of the predictions are going to be way different from each other. Okay, so what we should try to do is a balance between the two, where we have a balance fit. Some of the cases there might be a wrong classification, like one circle has been classified as a cross, or two crosses or one cross has been classified as a circle. So there are two misclassifications. But at the same time, it is not going to be overfit, or it is also not going to be underfit. So this overfitting and underfitting results in the next problem, which is called the problem of bias versus the problem of variance. What happens is, when we have a very, very simple model, we have a high bias, okay, and a low variance. That means we have the predictions coming close to each other, but all the predictions are going to be quite away from the bullseye or the ground truth. Okay, whereas when we are going to have an overcomplicated model, we are going to have the predictions coming closer to the ground truth, but they are going to be far away from each other. So this is the case where we have a high variance but a low bias for a very complex model. None of the cases, we don't expect the predictions to be so away from the ground truth, or we don't want the predictions to be so different from each other. Both these cases are not acceptable. Okay. Also, we don't have, this is the worst case, high bias and high variance. We are way away from the bullseye. At the same time, the instances, the predictions are quite far away from each other. So this is the worst case. And what we should try is a balance fit, where the model is a balance fit. Okay, there the model will come closer to the ground truth. There will be some discrepancies. It's not going to be very, very tightly close to each other, but it's pretty close to each other, right? So we should try to get as close to this situation as possible, where there is a low bias and a low variance, or at the very least, a moderate bias and a moderate variance. And how can we do that? If we can achieve, this is the curve where we have a model, complex model, which has, when the complexity increases, the variance increases. But at the same time, when the complexity is less, bias is high. What we try to do is a balanced model, which is going to have a moderate complexity. I'm not going to look at a polynomial dimension, a polynomial having a very high dimension, but maybe a polynomial which has a moderate dimension, maybe 3-4 orders. Okay, so this is how we should try to balance that. This is called bias versus variance trade-off. So what we are trying to do is, we are not trying to pull the bias to a very low limit. We are not trying to pull the variance as a low limit, at a very low limit. We are trying to balance the two. This is what is called a bias versus variance trade-off. Okay. Now we come to the next and the second last portion of the discussion, evaluating a model. And we are going to start with the classification model. This is very, very, very important. Please understand it very, very closely. Okay. And these terminologies are also very important, because you will often come across these terminologies when you come across the machine learning problems, right? So there might be, so first of all, just bear in mind, there is something called class of interest. Okay, class of interest. That is what particular class we are trying to predict. Okay, say for example, when I am trying to do the prediction of the outcome of a game. Okay, so I am trying to predict the win of a game, say for example. What is my class of interest? My class of interest is the class win. Okay, now that can be multiple situations. First, I am predicting a win, and actually the ground truth is also a win. The best possible case, right? This is called true positive. This is called true positive. Then I am predicting a win, but actually the ground truth is a loss. That means a particular game which I have actually lost, the prediction comes as a truth or a win. Okay, that means it is called a false positive. Okay, so I predict a win, get a win. It's called true positive. I predict a win, but actually it is a loss. It's a false positive. Next, I predict a loss. I predict that I will lose the game, but actually I've won it. It is called false negative. Last but not the least, I predict a loss and actually I have lost the game. It is called true negative. Okay, so very, very clearly, just keep this in your mind. The first term, true positive, false positive, false negative, true negative. The first term, this true and false, reflects whether the prediction and the ground truth has matched or not. If there is a match, then it is a true. If there is not a match, then it is a false. So this is the first thing. Okay. Second thing, positive, the second part, positive. Okay. When I am predicting the class of interest, so my class of interest is win. In both cases, I am predicting a win. Okay. Then the second part of the term is going to be positive. I am predicting the class of interest, which is win. So that means it's positive. And that is how the first quadrant is true positive. I have predicted and my ground truth both are wins. The second case, I have predicted win, but my ground truth is a loss. That means there is a mismatch, it's a false. But I have predicted a win, that is a positive, false positive. And if you look at this quadrant, in both cases, I have predicted a class of interest, not a class of interest. So I have predicted a loss. So that is a negation of the class of interest. So that is my negative. So the first one is a false negative. I have predicted a loss. Actually, it is a win. So it is a false negative. And the second one is a true negative. I have predicted a loss and it is actually a loss. It is a true negative. If you remember this, never ever you will be confusing the terms true positive, true negative, false positive, false negative. Because otherwise, even when I started with machine learning, initially I used to get confused. Which one is what? So if you just remember in this way, the first part of the term telling you whether is a match and a mismatch between the prediction and the ground truth. If there is a match, it is a true. If there is a mismatch, it is a false. And the second part of the term is positive if it is predicting the class of interest, and it is negative if it is predicting negation of the class of interest. Okay, so this is how you should determine. Now, this is called the confusion matrix, right? So if I look at this one, this is the prediction. So I had total 900 instances, okay? And for the 100 test instances, these are my predictions, okay? So in 85 cases, I had predicted a win and it was actually a win. So 85 cases of true positive, okay? In 4 cases, I have predicted a win and it is a loss. So it is a false positive, FP. There are 2 cases where I have predicted a loss, but actually there is a win. So false negative. And there are 9 cases where I have predicted a loss and it is actually a loss. So true negative. Okay. So I hope this is clear with all of you. Now, what would I do as a part of evaluation of the model? The first measure is the model accuracy. How many times I have classified correctly. And which are my correct classifications? These two ones, where the first term is a true positive and true negative, right? So I take a ratio of the true positive plus the true negative, and the denominator is the sum of all of them. True positive, true negative, false negative. So 85 plus 9, 85 plus 9 divided by 100. So 94 out of 100, which is 94%, or some people also write it as 0.94. This is my model accuracy. And obviously, as you can understand, the highest value of model accuracy can be 1 or 100%, where each of the predictions match with each of the ground truths. Okay? So this is one fundamental measure of a particular model, how good a classification model is performing. Okay? Now, coming to the next one, which is also a very important measure, which is called precision. What is the precision? What is the value of, that is the formula for precision? True positive divided by true positive plus false positive. So true positive divided by true positive plus false positive. That means what is the portion of win predictions? Okay, what is the correct predictions of win? What is the proportion of correct predictions of win? This is my precision. And in the same way, there is something called recall, which is true positive divided by true positive plus false negative. What is the proportion of actual wins? Okay, so what is the proportion of correctly predicted actual wins? This is the recall value. Okay, same way, we can also calculate sensitivity. This is a very important measure. True positive divided by true positive plus false negative. So again, sensitivity and recall, they are basically one and the same thing. Okay, and then we have something called specificity. So true negative, that is this one, true negative, right? Divided by true negative plus false positive. So the proportion of the true negatives. Okay, this is my specificity. Why are they important? Let me tell you. It might apparently look, it seemed to you, okay, fine. The accuracy is high. That means most of my most of my predictions are matching with the ground truth. So why do I need to bother about anything else? But there are certain cases where you need to really bother about it. Say, for example, when we are looking at a cancer prediction problem, the malignancy prediction of cancer cell, right? Then the class of interest is my malignancy, right? Now just think from this perspective. Say, for example, I have predicted a particular cell as a benign. Okay, I have predicted as a benign, but actually it is a malignant, right? So that means it's a false negative, right? Apparently the number may be less, maybe 1 or 2 cases we might have this. But the challenge is, in such a case, we have a big challenge. The problem is, in that case, we will have certain patients who will be screened as benign, but actually It is not, I mean, the tumor is not a benign tumor, or the cell is not a benign cell. So the further investigations will not be conducted on them. So that's going to be a problem. So what do we try to do? We try to go for more false positives. So we try to go for more conservative estimates. Even if certain cases we are predicting uh, as malignant and it is actually a benign, we don't bother about it, right? Because ultimately what is important to us is none of the actual malignant cases should be missed out as benign cases. That's why only model accuracy is not the only measure. We also look at the other measures. Okay, so that's also important consideration. The other, if we want to look at, instead of looking at the different measurements, and there is one more measure called F measure, which is basically a harmonic mean of precision and recall. It's just a robust, I mean, people call it as a, I mean, we look at it as a more robust measure of the model efficacy. Okay, so this F measure, right? So F measure is basically a harmonic mean of the precision and recall. Now, these are the different measures. We can look at it individually. But a much more holistic view, if we want to take a much more holistic view, then we'll refer to something which is called a receiver operating characteristic curve, or a ROC curve. What it does is very simple. For different models, it just plots the false positivity rate, which is basically the false positive divided by false positive plus true negative, with the true positivity rate, which is the true positive divided by true positive plus false negative. And what that signifies, the area under the curve, if we just plot that as area under the curve, indicates how good the predictive ability of the curve is. And the different indications are, if the ROC curve value lies between 0.5 to 0.6, it is assumed to be almost, I mean, like a sheer coincidence. It is not having any predictive ability. And as we push the ROC curve value towards, or the area under the curve value towards 1, the predictive ability of the classifier is considered to be improving. Okay, so always we try to push to a situation where the ROC curve, the area under the curve, is actually closing towards the value 0.9 to 1.0. Okay, so this is a very, very important consideration. The ROC curve, area under the curve, the AUC measure, is very, very important. Now, this was for classification. What about regression? So if we look at regression, and this is a very simple case of a simple linear regression, okay? Just the way we look at it is, the crosses are the actual values, okay? And based on the crosses or the actual values, we fit a model. Okay, we fit a model which is a straight line. And say, for example, this is my X, or the independent variable, and this is my Y. And there is some kind of a relationship we have come up with, X, Y is equal to MX plus C. Okay, and this M and X has some value. I'm not going to talk about that at this moment. Okay, some value has come. So what we have is, for each value of X, which we get from here, say for example, for each value of X we get here, we take a value of Y and map it here. And this is something we get on this one. Okay, on the line which has been fitted. Okay, now just look at it. This is my predicted value. This is my actual value. Okay, there is a difference between these two values. Both are numeric values, right? And there is a difference. This difference is called the error or the residual value. Okay, these are the residues. Now, a good model is definitely going to have the predicted values very close to the real values, okay, for all of the instances, right? So that the residual values or the errors are going to be as low as possible, right? So that is exactly what is being done here. Here we take a measurement. One very typical measure being taken is R square measure, which is basically SST, sum of squares total, divide minus SSE, sum of square errors, divided by SST. And what is SST? SST is basically the yi or the actual value of the y variable minus the mean value of the y variable. And for each of the instances, if we can do the square of that and do a summation of it. Why do we do a square? There is a logic behind it. Because some values might be less than the actual value, some values might be more than the actual values. If we don't take a square, or in some cases we take an absolute, what will happen is they may cancel each other, and what we may have as an overall value, the cumulative value, is very close to zero, which might tell us that the prediction is very, very accurate, but actually it is not so. So that is the reason why, so that it doesn't compensate each other, the values which are less than the actual value and the values which are more than the actual value, they don't compensate each other. For that reason, we either do a square of the negation, that means yi minus y bar square, summation of that for each of the instances. And what is the SSE? Yi minus y hat, the predicted value. So one is the mean value. From the mean value, we are getting the SST. And other one is the SSE, that is the sum of squared errors, which is the difference of the actual and the predicted value, or the y hat. Okay, sum of squares of the y hat. And this is my R square measure. Obviously, my intent will be reducing the R square measure. Okay, if it is closing towards the zero, that means my regression model is actually becoming more and more accurate. Okay, this is my regression measure. Next, we come to the clustering or unsupervised learning. That is a big challenge. And the challenge is when we do clustering. Say, for example, I have a set of instances. And here, what you see here in the slide is a very, very idealistic view. Generally, for the instances, there will be a lot more overlap. It is not going to be so segregated from each other. Each of the clusters or each of the segments are not going to be segregated from each other by so far. Okay, this is like an idealistic view which we are seeing. But there are going to be overlaps. Now the question is, when there are overlaps, or even in this case, how many clusters are we going to take? Because when we are getting a chunk of data, chunk of input instances, we really don't know. We have no clue. That's a completely unknown data to us, right? We don't know how many clusters are good enough to kind of segregate these instances. So it can be 4 clusters, or maybe I can just go with 3 clusters. I just club these things up and I go with 3 clusters. Or maybe I can go with 2 clusters. All these ones I have as 1 cluster, and all these ones I have 1 cluster. So I have absolutely no idea how many clusters can make the clustering most, what should I say, optimal. And what is the what is the definition of optimality? Just from a common sense perspective, what we can say is instances belonging to one cluster should be as close to each other. That means what we mean to say is instances in the same cluster should be as homogeneous as possible. And instances belonging to the different clusters should be as far away from each other. That means they should be as much heterogeneous as possible. Okay, so what we try to do is we try to have instances having very less intra-cluster distance and very large inter-cluster distance, right? This is what we try to do so that the clusters are segregated from each other, right? So that is the thing, but the point still remains. How many clusters? How do we know beforehand? There is absolutely no way. That is the reason why we say that clustering is in the eye of the beholder. It's a very, very relative thing. We really don't know how many clusters and what is the best possible way to do clustering, right? And still, say we have some way to measure the quality of the clustering, then the best possible way to measure is something which is called Shilute width. And what is Shilute width? Basically, it tries to differentiate the intra-cluster and the inter-cluster distance. Okay, it has two components. One component is that AI, which is based on the intra-cluster distance, the distance between instances belonging to the same cluster, that is AI. And the other component is BI, which is the distances between data instances belonging to different clusters. Okay, and the way we calculate is BI minus AI divided by max of AI comma BI. That is my Shilute width. In case I want to measure the cluster efficacy or how good the clustering is, we can measure using the Shilute width. Okay, and the other one, there is some other measure which is called the purity measure. Again, this is a very idealistic view. Say, for example, you have the input data set where you by chance you have the label for each of the data set. So it is basically a label set of data. Okay, and you just take the unlabeled portion of the data set and you apply clustering on the unlabeled portion. Okay, and then when the unlabeled portion you apply clustering, and for each of the instances you match, you apply a particular cluster. Okay, you kind of segregate to a different cluster. You try to see whether those clusters, the label for that cluster is actually matching with the labels which are there in the original data set. But mind it, this is applicable, this particular measure, purity measure is applicable only when you have an input data set, which is a label data set, and you are trying to apply clustering on the portion without the label. Okay, this is the ideal case. More often than not, you will not have a case like that. It will be a case you will have just a data set and you have to do the clustering. And in that case, the measure that we use is the Shilute width. Okay, so this is how we do the evaluation of a clustering model. Now I'm coming to the last portion, and say in case I get, and I'm going to stick to, for the time being, supervised learning only. Okay, say I get a particular model where the model efficiency or the model efficacy is not good enough. What do we do in that case? How can we improve the model? There can be multiple strategies. Okay, the most common strategy is something which is called ensemble or ensemble. Okay, what is that strategy? I come up with different training models. Okay, so either I can have different training data and train the same model, okay, or I can have different models also. Okay, so both of them can be variable. The training data used can also be varied and the model used can also be varied. And what we get as an outcome is the trained model, H1, H2 to Hn. Okay, and what do? We combine the model. We use some strategy, and we are going to look at a couple of strategy. We are going to combine the model and come up with a final output. What can be the final output? The final set of labels in case of classification, or the final set of values of the target variable, which is a numeric variable in case of regression. Okay, so we use a combiner to combine the outcome of the different models, and using the combiner, we come up with the final output. This is the basic concept of ensemble. Okay, you just use the different algorithms to do the model training. You combine the outcome of the model, and then you come with a final output. Okay, this is the basic concept of ensembling. And one particular type of ensembling, which is the bootstrap aggregating or bagging, uses the concept of bootstrap sampling that we have seen. Okay, so bootstrap sampling means we use the training data which has been drawn using the bootstrap sampling. And then what we do is we train the models using each of those bootstrap samples. And ultimately we get the outcomes, and the outcomes can be in the form of classes, or it can be in the form of numerical values, classes for classification and numerical values for regression. And then what we do is something which is called a majority voting. So here we talked about a combiner, right? So I get outcome from the different models. Say, for example, I have 3 instances. Okay, instance 1, instance 2, and instance 3. These are the 3 test instances, right? And for each of these models, model 1, or which is represented by H1, I get a set of labels. Say for 1 I get a A, for 2 I get a B, and for 3 I get a A. Okay, then again model M2, that is the second model. Okay, again I get a A. Okay, I get a B, and for model for the instance 3, I get a A. Say for example A. Okay, I have another model M3. I again get a A. Okay, I get a A, and I get a B. Okay. Now, say for example, I apply majority voting to get the final outcome, which is my combiner. Combiner is nothing but it applies the logic of majority voting. So what is my ultimate output? So M output is going to be the best of these 3. So A, it's going to be A because all of them are A. Here it is B, A. Majority vote is for B. So it is going to go for B. Then here it is going to have A, and B. So the majority voting is given for A. So my final set of classes or labels that I get for the test instances 1, 2, or 3 are A, B, and A. This is how the combiner can apply one strategy. Like here we applied the strategy of majority voting. Like this, we can also use the strategy of averaging for case of regression. Say for example, I get 3 outcomes as say 3.4, I get 3.6, and I get say 3.8. Okay, so how does my combiner combine it? It does an average of it. What is the average? This is my average, 3.6. I just do a summation and then I do the divide by the number of test instances. Okay, so my combiner just does a average of the outcomes from the different models. Again, What I am talking about here is a very, very simplistic view or a very simple strategy. What we do in reality might be much more complex. Okay. So this is the concept of tagging. Same way, we can also use the concept of boosting, where basically certain learners or weak learners or weaker models are also boosted, or their performance is being boosted by using resampled data. A fresh sampling is being done, and using that a resampled data, with that it is being trained, and then what is being done is, instead of average voting, or rather averaging, it does a weighted average. What is a weighted average? So there are, say, for example, few models, model 1, model 2, and model 3. And each one of them, for example, there is a specific value of accuracy which has been obtained. Okay, and say model 1 has given a little lower accuracy, say 0.7. Okay, model 2 has given a little more accuracy, say 0.85, and the highest accuracy has come from model 3, say for example 0.95. Okay, what you do is, instead of doing an average of the outcomes from these models, you take a weighted average based on the performance of each of the models. And the weaker models are being compensated, I mean, they are being penalized, and the stronger models are rewarded. So more weight is being given to the stronger models, and less weight are given to the models having the lesser this thing accuracy, or weaker models, right? So this is the concept of boosting. So these are different techniques which can be used. Other than that, this is ensembling is one strategy. Other than that, there can be other multiple strategies which can be used to kind of improve the performance of the models being trained. Okay. So with that, I think I have covered more or less what I had for today. And we have seen the whole gamut, starting from selection of the model based on what type of problem we are looking at. And then once we select the model, we use the data, we divide the data into training and test data for supervised learning. We train the model, and then we evaluate the model using different types of measures like accuracy, the sensitivity, specificity, F-score, or we use a visualization technique like a ROC curve, or use the AUC, the area under the ROC curve, and we evaluate the model. If we see that the model is not performing up to the mark, then what we do is we kind of try to improve the model performance either by ensembling or by some other techniques, like we can do parameter tuning, we can do hyperparameter tuning, and all those stuff out there, right? So this is the whole gamut, starting from understanding, starting from yesterday. So we have a problem. So we go get some data. First of all, we need to collect the data. We have to explore the data. We have to do different corrections in the data based on whether there are missing values, whether there are some outliers. With that corrected data, we then start the model selection process based on the model problem type. If it is a classification problem, or if it is a regression problem, we select different models. If it's a classification problem, we can go for a NB or a need-based model or a SVM model. If it is a regression, we can go for a regression model, like multilinear regression model. If it is clustering problem, we can go for a K-means or a K-midwives, right? So we select the model. Then what we do, if it is a supervised learning, we train the model. What do we do as a part of model training? Basically, the algorithm is basically aligned with the data which is given. Okay, and then we have to evaluate, because we don't know how good the model is. We use a portion of the segregated data, which is the test data, for which we know the ground truth. We use that and evaluate the model. What are the parameters we use? What are the metrics that we use? Metrics like accuracy, sensitivity, specificity, and all this stuff. And then If we see that the model is not performing well, we use techniques like enabling to improve it. Okay, so this is the whole journey that we take. Okay, so I will pause at that. Again, I think the references, standard references, I can suggest. If it is for the beginner level, like what we are going in this particular FDP series, the textbook by co-authored by me, you can refer to that. If it is more for the lab purposes, there are some lab or some workouts which are there in this book also. At the end, all the functions, all the processes, all the different concepts, you will get code implementation using R and using Python at the end of the book in the form of appendices. Okay, so you can either use that or there is one more very useful book, but that is specifically for Python. There are good projects which are given as a part of this book. Okay, and a very step-by-step way to explain how the projects need to be executed. Okay. Similarly, there are books for other platforms like Python or MATLAB. You need to just look through. Since in most cases I go for Python and R, I can recommend books for Python and R only. And once you have already come over and you have already got this understanding, the book, which is like a classic book for machine learning, and all advanced learners in machine learning should definitely refer to this book, is the book by Tom Mitchell, like the father of machine learning, Tom Mitchell. You should be going through that book once you are well versed with the common concepts that we are talking about. Okay. So that's all for today. I think today I am able to complete in time, which is the ideal thing we try to do. So if there are questions, maybe I can take a few questions, Dr. Ravinder.
Yes, sir.